All right, guys, so as we finally get to wrap up 4.2 and the concept of the mean value theorem, we are going to wrap it up with a little introduction to the term antiderivative, which is going to be a extremely huge part as we close up calculus for this school year in chapter 5 with integrals. But first and foremost, what we're going to look into is a little mini goal for the day. Our goals overall, are still using the mean value theorem, identifying it, and in a way to lead us into bigger things is what we are doing today. And so all of that big goal still led us into what today is all about, which is finding a function based on the function's derivative itself. Okay, so we're going to identify what the function is based on what we are given in terms of its derivative, okay? So I have a key little note I want you guys to take home. Functions with the same derivative differ by only a simple constant, all right? Let me say it one more time. Functions with the same derivative differ by only a constant. So let's say, for instance, here that I have a function, I don't know, f prime and g prime, okay? So let's say f prime of x and g prime of x are both the same things. So that means the derivative of f and the derivative of g are the exact same thing. All right. The only difference between f and g is going to be the fact that there is some value, we'll call it c, that is being added or subtracted to one of the functions that make them somewhat different somehow. Because if they were the same function, then they wouldn't be two different names, right? So there's just some constant that makes things somewhat different. So if it's like 2x plus 1 or 2x plus 3, the only difference is the constant itself, okay? And that's going to lead us into a great first example of today and to show us where antiderivatives actually come from. So example number 1 says, find the function f of x whose derivative is simply sine of x and whose graph passes through the point at 0, 2. Okay, so let's think here for a second. Okay, so f has a derivative that is sine of x. So we got to kind of think about it to ourselves is what was the original function such that when we took the derivative of it, we got sine of x. Well, we got to kind of think back to what we know about derivatives, okay? Remember for a sec, when we are dealing with cosine and sine have that relationship within tangent or within derivatives. And so the derivative of cosine, don't forget, is negative sine of x. So that's kind of close, but it's not exactly there. So if cosine of x's derivative is negative sine of x, well then that means negative cosine of x has a derivative of positive sine of x because of what would have happened within that particular chain rule. So since f has the same derivative of, let's call that function g of x, so we know g of x for sure is the function negative cosine of x because let me erase it real quick because I kind of forgot the negative originally. We know that g of x is negative cosine of x. So that's what's going to give us a sine x. So to kind of make this different, we know that f of x had to have been negative cosine of x as well too, but there is some different constant that was a part of it as well. And so the only thing that we got to kind of figure out here is, well, what the heck is the constant going to be? And that's where the restrictions of passing through the point 0,2 come into play. Because for the function f of x, when x is 2, or x is 0, y is going to be 2. So we know that f of 0 should equal 2. So negative cosine of 0 equals 2, or plus C equals 2 in this example. So the entire function f of x equals negative cosine of x plus c equals 2. So now we're just basically just solving for c itself. Well, this really is just negative 1 because cosine of 0 is 1 and times the negative is negative 1 plus c is equal to 2. Well, actually, c equals 3. So just kind of wrapping it up, the function completely is negative cosine of x plus 3. All right, so we kind of worked backwards. We kind of thought to ourselves, all right, well, what function gives me a derivative of sine of x? Well, we don't have anything exactly that tells us that, but if cosine's derivative is negative sine of x, that means negative cosine of x is a positive sine of x for its derivative specifically. And what we just found out here, guys, was our first example and first dive into what the antiderivative is. So, by definition, the antiderivative. So let's say, for instance, a function, we're going to call it capital F of x, is that word antiderivative of a function f of x if the derivative of the antiderivative is equal to f of x for all x inside the domain. Okay? So if we will say we have an antiderivative if the derivative of the antiderivative capital F prime of x equals the original function f of x itself. Okay? All right, guys, so we're gonna look into one final example of how to utilize this a little bit more so into application. And so what I am going to look into for this example is find the velocity and the acceleration of a body falling freely from a height of 0 meters under each of the following conditions. So here's our base for this. So we want to find out what the velocity and the position was based on the following conditions. Remember, position, derivative becomes velocity. Derivative of velocity becomes acceleration. So what we are looking into for condition number 1 is with the acceleration being 9.8 meters per second squared, and the body falling from rest. All right, so let's look into this first condition first and foremost. So once again, remember, velocity in this case would be the antiderivative of the constant 9.8, all right? So let's think that for a second. So velocity, v of t, would be the equals the antiderivative of a of t, which equals 9.8, all right? Which equals 9.8. So what we need to now look into account, well, first off, what is t? All right, because t is always a part of it. When we're dealing with things that are moving, it's time. So in this case, it's falling from rest. So that means t is going to be 0. So that's kind of nice to deal with here. So basically, we've got to think to ourselves, v of t. What would v of t be if the derivative of v of t equals acceleration. So v prime of t equals acceleration, which equals 9.8. Well, what was v of t if the derivative was 9.8? Well, if it's in terms of time, to get a constant as a derivative, that means there had to have been a single variable with a 1 exponent beforehand. So that means v of t had to have been 9.8 times t specifically. But don't forget, it's plus whatever constant could have possibly been there as well, okay? Because you could have taken a constant of anything and the derivative becomes 0. So don't forget that, please, 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 please. So now we got to kind of think for our, to ourselves for a second. What's happening to make this a completely true statement when this is all said and done? So, well, when is, t going to be 0 in particular in this case? Well, t is 0 when it's at rest, and then the velocity is going to be 0 when c is 0 as well, all right? So, if t is 0, so v of 0 in this particular case becomes 9.8 times 0 plus c. So I basically, got to think to ourselves, since it's coming at rest, the velocity when it's resting is 0. So I got to figure out what is c when velocity is 0. So in this case, I really just need to take 9.8 times 0 plus c and set it equal to 0, or c being 0 in this case. So since c is 0, the full velocity equation is going to be 9.8t plus 0. Well, that's not anything but just 9.8t. So that is our velocity in this case. That's velocity. Now let's find position. Well, now remember, position should be the antiderivative of velocity, right? So it should be the antiderivative of velocity. And so in this case, we should be looking at saying that s prime of t should equal v of t, which in this case was 9.8 times t. So in order to find s of t, I need to take the antiderivative of 9.8t. Well, basically, you have to think to yourself, what did you do to go from to 9.8t? Well, that means you have to kind of think backwards, right? So that means I ended with an exponent of 1. That means the step before that should have had an exponent of 2. And I would have multiplied it by whatever that value is before 9.8 got divided by or multiplied by 2. So instead of multiplying 9.8 by 2, I will divide it by 2 and get 4.9 t this time squared. And you can always double check. 2 times 4.9 is 9.8 minus the 1 becomes t. And so this is really 4.9 t squared plus c. And so once again, we are concerned with, what's happening when t is 0. So s of 0 is going to equal 0 in this particular example if I'm not really concerned with c. So I need to find out what is c going to be. Well, in this case, c, 4.9 times 0 squared plus c equaling 0. Well, this is just going to be c equals 0 once again. Full value for s of t is going to be 4.9 t squared. What I want you guys to do as a kind of a check for yourselves is do the second condition, all right? Do part B on page 201 and cover up the answers, all right? Give it a shot on your own and then reveal the solution to see if you guys got it on track. You guys have a great one. On to the next one.